Hi, everyone. Thanks for joining us again. So now we have Dima Kogan, who's here to tell us about private information retrieval. Dima is the Chief Technology Officer and the co-founder of Orem, which is a startup in the blockchain space. He did his PhD at Stanford as a student of Dan Bonnet, and during this time he received several Best Young Researcher paper awards. And his works focus on applied cryptography, on computer security and blockchains. And today he'll tell us about private information retrieval. So Dima.
Hi, Mar. Hi, everybody. Thank you so much for inviting me to speak here in the Winter School. I really wish next year we could all meet in person here in Israel. Today, I will be speaking about private information retrieval, which is a topic I really like and I'm really excited about, both because it has a really cool theory, but also because it has really nice applications to practice. And I hope to talk to give you a good picture of this topic today. So to start off, what's private information retrieval? It's a cryptographic protocol introduced by Shor, Goldratt, Kushilevitz, and Sudan in '95 that allows users to read records from a public database without the database learning which records the users are interested in. So you can imagine a lot of applications for this setting. For instance, whenever the user's query contains some sensitive information about the users, this could be a user querying like a medical encyclopedia, and his query contains some information about the condition the user has. Or maybe the user wants to query some financial database and the query contains information about the user's financial interests. But also PR is very useful as part of larger privacy preserving systems, for example, systems for private video streaming or metadata hiding messaging. And today, throughout the 2 hours of this talk, I'll try to cover both some classic results about PIR. So in the first half of the talk, I will talk about the model, some basic classic schemes, and some extensions that are actually kind of bridge the theory to practice. And then in the second half of the talk, I will talk about more recent works and efforts that try to reduce the amount of computation that PIR requires. And I'll also talk about a couple of classic results there, but also focus on some recent works that I've worked on together with my co-authors, Henry Corrigan Gibbs and Alexandra Hensinger. So we'll start with the first part, which is introduction to PIR. So what are the two main requirements of a PIR protocol? First, we require correctness, which informally means that the client should learn its bit of interest, either always or at least with some overwhelmingly high probability. And second, we require security, meaning that a malicious server should learn nothing about which record the client is reading. And if we just require those two requirements, then there's actually a trivial protocol, a naive solution that meets both of those. Namely, the client can just download the entire database, store it locally, and query it locally without ever contacting the server ever again. And this would guarantee perfect correctness and perfect privacy, as basically the client will send no information about his query to the server. The downside, obviously, is that this requires a very large communication cost. So downloading the database and storing it could be prohibitively high in most settings. So to make the problem more interesting and more relevant to practice, we'll actually look for protocols that try and minimize the amount of communication between the client and the server. And in general, there are two main approaches to PIR. The first approach, introduced in that same paper that posed the problem, the first approach basically solves the problem by replicating the database between two or more non-colluding servers. And in this setting, we'll see you can actually get information theoretic security. And then the other approach, introduced by Kushilevitz and Ostrovsky in '97, doesn't actually require any replication of the database, but it does require making cryptographic assumptions, and the resulting security is computational. And I want to give you now a taste of each type of construction. So let's start by seeing a two-server private information retrieval protocol. And here we'll assume we have two servers that are non-colluding, meaning that they do not kind of cooperate to try and break the user's privacy. Syntactically, such a PIR protocol consists of three efficient algorithms. The first algorithm is a query algorithm, in which basically the user inputs the desired index of the database it wants to read, and the algorithm outputs two queries, one to each of the two servers. Then the user sends those queries to the server, and each of the two servers runs the answer algorithm, which takes as input the database X, which we model here as an n-bit array, and we'll see how to relax this requirement later on. And the answer algorithm outputs the answer that the server sent back to the user, at which point the user runs the reconstruct algorithm that takes as input both responses from the servers and outputs the value of the desired bit. And we can now kind of state our requirements a little bit more precisely. So we talked about correctness and said that we want the client to learn its bit of interest. We can, in this setting, we can even require perfect correctness, meaning that for every size of the database, every database and every index I that the user wants to read, if we just follow the protocol kind of query, generate the queries, have the servers answer them, and then run the reconstruction method, then the output value of the reconstruction method will be exactly x sub I, the ith bit of the database. Now let's see security. So we said we want the servers to learn nothing about the client desired bit. And here in the two-server setting, when we assume that the servers are non-colluding, what we basically require is that the view of each server on its own doesn't reveal anything about the desired index. So if we look, let's say if we look at the view of say the first server when the client is reading bit I, then that view should be either computationally indistinguishable or actually basically statistically identical to the view of the server when the client is reading some other bj. So the view is the same whether the client reading I of j, and therefore the server doesn't know which index the client is reading. And syntactically, it just means that if we run the query algorithm, generate the two pairs of query, if we look at each query on its own, say either to the left server or to the right server, then the distribution should be indistinguishable. And and this is kind of captures let's just make sure that we see how does this definition capture the fact that we're talking about non-colluding server. Notice that we only look at one query at a time. So the marginal distribution of each query is indistinguishable. But if we look at both, queries together, which models the hypothetical scenarios in which the servers collude, then all bets are off and security is no longer guaranteed. And as I said, we can talk about either computationally indistinguishable distribution, and this would be a computationally secure PIR scheme, or statistically identical distribution, and this is where we get perfect security. So are there any questions about the model and the definition, perhaps?
No questions till now.
Great. So let's then move on to see a construction. So the first construction is from this original PIR paper, and the way that we set things up is that we'll basically view the database, which is an n-bit array. We'll view it rather as a matrix, as a square root n by square root n matrix over Z2. So just kind of a square matrix of bits, and all the database records are kind of placed into this matrix. And then in this view, basically the input of the client is some coordinate in this matrix. So a pair I comma j, which is just an element of the matrix that the client wants to read. So let's see how the protocol goes. So first, what the client will do in the query algorithm is it will sample two random column vectors of length square root of n. That each of them will be random, but together their XOR, so kind of the sum modulo 2 element wise, will be the jth unit vector. So it will have 0 in all square root n positions except in position number j, which, remember, this is one of the indices that the client wants to read. That will have 1 here. Then the client sends those two query vectors to the two servers, and each server takes a matrix vector product between the database matrix and the query vector, and the result is another square root n vector that the server sends back to the client. And now the reconstruction procedure is that the client sums or XORs the two vectors, the two square root n vectors, and then just reads off reads off the ith element of the resulting vector as its output. Yeah, so just a single bit output here. And let's make sure that this protocol indeed meets all the properties that we want. So in terms of correctness, this just follows from the linearity of the matrix vector products. So if the two query vectors, they add up to a unit vector, then the resulting answers basically add up to the jth column vector. And then when the client reads off the ith element, you just get the element xi sub j, which is the bit of interest for the client. And in terms of security, because each of the two queries is a uniformly random vector, completely independent of the client's input, then we get perfect security as long as the servers don't collude. And the efficiency of this protocol, well, we have square root n vectors going back and forth. There's totally 4 of them, so we get order of square root n communication complexity for the protocol. And it actually, continuing this line of work on 2-server PIR, we saw on Sunday in a Let's Talk a different construction that used distributed point function, where you can compress all those query vectors to be only of logarithmic length, which gives us logarithmic communication complexity. But then we get computational security because those DPFs require using PRGs and computational assumptions. So basically, following this initial work on 2-server PIR, there's been a very long line of work gradually improving the state of the art on multi-server private information retrieval. So here I talked only about the 2-server case, but there's also a lot of improvement in the multi-server case and there's more than 2 servers. And nowadays we have informationally theoretic secure PIR protocols in the 2-server setting with n to the little of 1 communication. And if we're willing to make computational assumptions, then these constructions from distributed point functions allow us to get even better communication complexity, logarithmic communication complexity. So that's kind of the state in the 2-server and the multi-server world. Let's now see how does PIR work in the single-server setting. And this was introduced by Kushilevitz and Ostrovsky soon after the original PIR work. So here again, we'll view the database as a matrix, a square matrix of size square root n by square root n. And the main idea that instead of secret sharing the query, that unit vector, as we did in the 2-server case, we'll basically encrypt it. And specifically, we'll encrypt it using linearly homomorphic encryption. And linearly homomorphic encryption is basically allows you to do to compute addition of ciphertext to get a ciphertext which encrypts the sum of the underlying plain text. And so we can kind of do linear algebra on encrypted messages. And this type of encryption we can actually build from a wide range of public key assumptions like DDH, quadratic residuosity, learning with errors. From a bunch of public key assumptions. So now that we have such a linear homomorphic encryption, what we'll do is that the client, as before, kind of generate a unit vector with 1 in the jth position and encrypt it element-wise using linearly homomorphic encryption. And they will then send this query to the server, and the server will take a matrix vector product. And because the encryption is linearly homomorphic, and the database is given in the plane, then you can kind of do this matrix vector product on the encrypted query and get the encrypted response. And this encrypted response will now have the desired element xi sub j, xij in the ith position. So the client receives this response. It just decrypts this ith position from the response vector, and this gives it the bit of interest. And the security here follows from the security of linearly homomorphic encryption from one of those assumptions. The communication here is that now you need to send just a square root n ciphertext and then download square root n ciphertext. And if you have a linear homomorphic encryption with kind of compact ciphertext, then you just get order square root n with some dependence on the security parameter. So in the single server setting, there's also been a lot of improvement. I presented this scheme was square root n, but you can apply different types of, say, recursion techniques and other stuff, and you can get polylogarithmic communication complexity from a wide range of public key assumptions here in the single server setting. So yeah, that's kind of the basic. We saw one construction in the two server case, one in the single server case. Before we move on, I just want to do a brief comparison between PIR and a different primitive that we've seen in the school this week, which is oblivious rel. So both of these types of schemes or protocol, in some sense, they both allow, their goal is to hide the data access pattern. They're allowed to privately read things from some remote storage. But there are quite a few differences between those two protocols that make them applicable in different scenarios. So one of the main differences is that in PIR, the database is completely public, and you don't need any kind of secret state in order to run the protocol. So any client can come and just start interacting with the server and do a private query, and you don't need to coordinate beforehand or hold some private state. So the protocol kind of trivially supports unlimited number of clients, and there's no need in cooperation or in trust between the different clients. In Orem, the situation is a little bit different. Here, the database is encrypted, and moreover, it's kind of permuted and reordered all the time based on some private state that the client needs to hold. So in order to read elements from the remote storage, in Orem, the client needs to hold some kind of secret key, some kind of secret state. And therefore, the protocol basically targets the setting in which we have a single client that outsource its storage to some remote server. Well, you could ask, why can't I just then support multiple clients by sharing this state between multiple clients? And the problem here is that one client can give its state to a different client, and then this other client can also query the server. But the key point is that security only holds as long as you keep the state private. So if you have like mutually distrusting clients, they can't just share state, because otherwise the query of one client will not be private to a different client. So I think maybe the best way to say it is that you can think about PIR as allowing private access to public data, whereas in Orem you kind of outsource your data, but your data is still yours. So it's kind of private access to private data. And in the setting, there's actually there's another difference, is that PIR in the setting it's not completely well defined to talk about rights, because if you change something in a database, then it's public, everyone can see what you change. So we usually focus only on reads, even though we can talk about kind of specialized setting to talk about rights, but usually it's just reads. And in Orem, the client can manage this remote storage. It can read, it can write. And the Orem scheme support both types of operations. So yeah, I just wanted to contrast the two types of scheme that we've all seen this week in the winter school. Any question either on this or the constructions?
Yes. So there are a few questions. So the first question is regarding the model. Do we care about server computational complexity in terms of?
Yeah, that's a great question. We actually, in the second part of the talk, we'll talk specifically about this. So, initially, the main parameter of interest is usually the communication. The protocols mostly try to optimize this, but obviously computation matters, and yeah, we'll talk about it in length later on.
Okay. So another question is, do we always talk about PIR where the database is an arbitrary string, or can we somehow take advantage of the fact if the database has certain structures?
That's a good question. So usually as far as I know, usually the PIR protocols don't exploit any particular, generic protocols don't exploit any particular structure. And you'd want your protocol, you'd want your cryptographic protocol to support any database that you want. And we'll talk a little bit more about other structures of the database. So not only, we'll talk about key value stores and this kind of stuff a little bit later on.
Okay. So the last question, this is about two server PIR. So are there, say, more efficient constructions if not, I mean, both the servers, they store shares of the public data instead of storing, as in replicating the public data?
I see. So if you're willing to share the public data, I'd have to think about it. Maybe think about it offline. It doesn't. I don't have a good answer at the top of my head.
Oh, okay.
I'll try following up on Slack. Cool. Yeah. Thanks for the question. Yeah. Great questions. Okay, so let's talk now a little bit about extensions that try to make the PIR model a little bit more realistic. So one direction that I want to talk about is that, you know, most interesting databases in practice are not really n-bit arrays. You know, usually you don't really care about specific bits. You want a little bit more rich interface for your database. And we'll talk about two pretty simple extensions. One is that how just to support longer database rows. So the record, it's still an array, but the rows can be longer, the records could be longer. And then we'll also talk about how to support key value lookups, which is something very useful, you know, for databases. And then the second type of extension I would like to talk about is, you know, so far we've only talked about the client's privacy. We didn't make any requirements that would give some privacy benefits to the server. We have assumed that the database is completely public. And I want to talk about an extension which actually allows the server to get some privacy benefits as well as part of the protocol. So, you know, the first extension, it's pretty straightforward. So let's assume now we have a database that still has n records, but now the records are L-bit long. So, what we'll do is we'll have the client query each bit of the record using a PIR scheme for a single bit record. So instead of the server just, you know, viewing the database as one array of L-bit records, we can just view it as L databases. And, you know, the first database stores the first bit of all the records. The second database stores the second bit of all the records, and so on and so forth. And just to avoid confusion, here, all those, you know, sub databases, they're all stored on the same set of servers. So if we're in a single server setting, all those databases will be hosted by that same single server. If we're in the multi-server setting, that each server will hold, you know, a replica of each of those, you know, bit databases. So just to avoid confusion, these are not more servers. These are just, you know, individual databases on the same servers. Cool. So how does the protocol work? Well, the client wants to read, you know, the ith record. So it used the base PIR scheme that allows you, you know, that's just for single bit records, just generates this query and sends it to the server. And then the server just takes the query and runs the answer algorithm with respect to each of those shards of the database. So basically it responds to the query with respect to the first bit of the records, then to the second bit of the record, and so on and so forth, and then sends all L responses back to the client. And, you know, just a quick check. Notice that we only need to send a single query because, you know, it's the same index of the record that the client wants to read. You know, it wants to read the ith first bit and the ith second bit, and so on and so forth. So only one query the client needs to send, but the responses are obviously you need one with respect to each of the bits. Then the client just runs the reconstruction algorithm bit by bit and outputs the record. So let's see, the communication here is that if the original scheme has upload U of n and download D of n, then the new scheme will have the same upload, but the download will be multiplied by a factor of L. Yeah, so that allows us to read larger records. Now let's see how we can use PIR, you know, to implement richer data structures. So here, in many applications, we would want to query either a set, so maybe a collection of keys, and the client wants to learn whether a particular key is in that collection, or a dictionary where there's a key value store, and the client holds a key, and it wants to get privately fetch the corresponding record. So the general idea, again, it's pretty simple, but I think it's quite useful. So the general approach is that will use a standard data structure for that problem, so either a binary search tree or a hash table, and then the client will run the lookup algorithm for that data structure. It'll just wrap each probe into the data structure using PIR. And this will guarantee privacy of the entire process. There's a little bit, a couple of caveats, and as we'll see now in the example. So the simple example, let's say we want to implement a set. So the server has some collection of keys, and the goal of the client is to learn whether a particular key is contained in that set. So what we'll have, let's just, the server will just store this set as a sorted array of keys. So we'll have, we already have a PIR scheme for larger records. Here we'll store all those keys as records in an array, sorted, in lexicographic order. And then we'll use this idea. We'll run, the lookup algorithm is just, binary search, wrapping each probe with PIR. So the client holds some key. The first thing it will do, it will run the PIR scheme to read, record n over 2, with k here being the server's input, the database. So the client privately learns k n over 2, the middle key. Then it checks it, just binary search tree, compares it to its key. It say in this case, the key is smaller, so the client then reads record n over 4, and again compares, and just continues its binary search until it finds the key of interest. Here's like one caveat that I hinted to. Even after the client finds K, it still needs to complete all rounds of the protocol to avoid, early termination, leaking something about the record that it's reading. So, here the client needs to complete all log n rounds of the binary search, and then it finds the record of interest. So this is a very simple data structure, just a sorted array. If we use a little bit, more complex data structures such as hash tables, or use perfect hashing, we can actually solve this problem of private key value lookups or private sets with only 2 queries between the client and the server. But the general paradigm is the same. Cool. Yeah, that's the second extension. And then the third extension I want to talk about is this idea of how to guarantee some privacy also for the server. And it's not even completely immediate how to define it, but the way we should think about it informally is that after each execution of the PIR protocol between the client and the server, the client should learn at most 1 record in the database. This is, you can imagine, if maybe the server charges the client per query, but it still wants to provide it privacy. So it knows, if they ran the protocol once, then the client learns only 1 record, and if the client wants to read more, it needs to pay more or something like that. And the very cool tool that we can use to implement this requirement is called oblivious pseudorandom function, or an OPRF. So an oblivious pseudorandom function is this tool that was implicitly introduced in the work of Naor and Reingold, and then defined in the work of Friedman, Ishai, Pincus, and Reingold in 2005. Is a cryptographic protocol, also a cryptographic protocol with a client and a server, where the client has some input X, and the server holds a key to a pseudorandom function, a key to a PRF. And then the client and the server engage in a protocol, and at the end of the protocol, the client learns the value of the PRF on its input X, and the server learns nothing. And in particular, the server doesn't learn which point the client wants to evaluate the PRF on. So yeah, this is a very neat primitive. We can build it, from discrete log type assumption, and also from RSA assumptions and post-quantum assumptions. It's pretty efficient in practice. And let's see how to use it to implement symmetric PIR. So what the server will do, the server will encrypt the database record by record. So here the server encrypts x0, x1, sorry, it should be x1 until xn. And the keys to the encryption, so each record will have a different key, and the server will generate the encryption keys using the oblivious PRF, or just by locally evaluating the PRF. The server holds this key, k, it computes the value of the PRF on index I, and this is the secret key that it will use to encrypt record I. And then the client, to allow the client to retrieve record I, the first step will be that the client and the server will run the regular PIR protocol that doesn't guarantee any privacy for the server, and the client will learn the value of the ith record, this E sub I. But because this PIR protocol doesn't guarantee privacy for the server, as part of this protocol, potentially the client learns some additional information, but this is now, either partially or fully, it can learn other records in the database. But the key point here is that this database is encrypted. And then in the second step of the protocol, the client and the server will run the OPRF protocol, where the client, inputs I, and the server inputs its key K. And in the end of this protocol, the client learns the secret key S sub I, which is the value of the PRF, which is the encryption key for that record of interest for the client. And then the client can just decrypt the record using the secret key and output its record of interest. So let's just see why did we get both? Now we need privacy for both the client and the server. So the client's privacy follows from the security of the PIR and the security in the OPRF. Both of them guarantees that the server learns nothing about the client record of interest. And the server's privacy now follows from the security of the OPRF and the semantic security of the encryption scheme. So the OPRF guarantees that the client learns only one encryption key or decryption key. And the PIR, the semantic security guarantees that as long as the client didn't learn the encryption key, all the other things that might have leaked during the execution of the PIR protocol don't reveal the actual database items to the client. Yeah, so I think it's a pretty neat idea how to implement symmetric PIR very efficiently from regular PIR. Cool. Any questions on the extensions?
Yes. So there are questions pertaining to PIR with keywords. So one question is, are there any single round protocols for this?
So notice here that the two executions of the PIR and the OPRF can actually, can be interleaved, like can be run in parallel, right? Like the input to the OPRF doesn't depend; it only depends on the index and not the output of the first round. So in fact, you can run them together.
No, I believe this question came in slide 26.
Oh, sorry. See. Oh. Single round. I see. So I mentioned that you can do two queries. If you can do a single query, I guess it depends on the communication, because at least theoretically we always have like I guess it depends on the communication, because there's always the trivial protocol of just downloading the entire collection. But it's a good question of, can you do actually very efficient single round protocol? I'm not sure. I don't know of those.
Okay.
It's a very good question.
Right. One more is there not a problem with the second extension in that if the second query does not include n to the power 3 by 4 as one of the requested indices, like in the two server model, the server can learn the entire and the entry we're looking for as in the first n by 2 entries, or does this have to be like in the single server model necessarily?
So this, if we're talking about this extension, is the PIR, is this one, right? The PIR by keywords. So I think here this can be applied both in the two server and in the single server setting, and it just means that that what you need to be careful, like you need to make your lookup algorithm oblivious, in the sense that, as we've seen, like the number of queries does not depend on what you're looking for, and each query will not leak any information, because we'll run it using PIR, whether it's to a single server PIR or two server PIR.
Okay. So that's that. And I had a basic question. So when you talk about PIR with security for the server, how is this different from oblivious transfer?
Yeah, that's a very good point. So you can in some sense you can view this as an 1 out of n. You can view it as like a 1 out of n OT, because I think it's equivalent. It's just that, usually it was defined, in the, at least initially in the multi-server setting. So in OT, we usually think about it in the one server setting. Exactly. So you can think about it it's kind of I think in the original papers, you kind of distributed OT.
Okay. All right. We just got one more question. What is the communication complexity of the OPRF protocol?
So it's very efficient. It's like in some sense, if you do it from something like DDH, then if you build it from one more discrete log assumption, then it's basically like a handful of group elements that you need to send. So something like basically like proportional to log n and the security parameter, like linear. Very efficient.
That's all the questions.
Cool. Thanks for the questions. Let's then move on. Now we can get back to this question that someone asked earlier that I plan to talk for the remaining time in this hour and the next hour is this issue of the computational complexity of PIR. And indeed, if you look at those protocols that we presented, the single server protocol, the two server protocol, they all had this property that the server needs to kind of linearly scan the entire database to respond to a query. Particularly, the server needed to do this matrix vector product, and which is of course at least linear in the size of the database. And having to run this expensive online phase. For each query, it's actually a barrier to deployment, right? Because usually when we think about databases, we want queries to be fast. We like databases store indices so that you don't have to scan the entire database to answer to a query. And here, this computational cost is expensive, and indeed, it turns out that this is necessary. So Beimel, Ishai, and Malkin showed in 2004 that the server must do a linear amount of work to respond to a query, which is a little bit discouraging. And the intuition behind this lower bound is that if while responding to a query, the server doesn't touch a particular bit in the database, then somehow the server learns that the client can't be reading that record of interest. And this is a very rough intuition, but it turns out you can generalize it even if you have many non-colluding servers, and even if you're willing to make cryptographic assumptions. So it's a very very strong lower bound. And in the remaining time of today's talk, I will actually talk about several approaches that try and circumvent this lower bound and somehow reduce the computation required for PIR. And specifically, we'll talk about a couple of classic approaches, and then the most of the time I'd like to spend on this recent approach that I've worked with together with my colleagues. It's called offline-online PIR. So any questions perhaps on or kind of where we're going on this problem?
No questions still.
We're good. Great. So the first approach that tries to reduce the computation of PIR, it's called batch PIR, and it was initially introduced in this batch codes paper by Ishai, Kuchilevitz, Ostrovsky, and Sahai in 2004. And here how this works. So essentially, the client and the server, they pre-agree on some, this is one variation of it. The server and the client agree on some random partition of the database into queue buckets. Let's just think of them as equal size. And then when the client wants to, this batch PIR scheme will allow the client to read multiple records from the database more efficiently than just run the PIR scheme one by one on each index. So the key thing is that if we start off with a random partition of the database, then with high probability over the choice of this random partition, then for any fixed sequence of Q indices that the client wants to read, then by the standard balls and bins argument, no bucket will contain more than something like lambda log n indices, lambda being the security parameter. So you actually get like negligible probability in lambda to one of those buckets kind of overflow and contain more than this number of input indices of the client. And now the idea is that the client can just query each bucket lambda log n times and embed its index of interest into those lambda log n queries. And because of this load that doesn't exceed lambda log n, then this will be sufficient to read all the indices of interest. And the benefit, where does the computational benefit come from? The fact is that now you only run PIR on much smaller databases. So you run PIR on databases of size n over q, and this would be more efficient. So let's maybe see an example how this works. So the server partitions the database using, say, some hash function. I won't go into the details. Just think about maybe they use a random oracle or something like that. And then the client just needs to have a description of the hash function or access to the random oracle. So in this example, let's say we have a 12-bit database. We have 4 buckets. We have like three records in each bucket. And now when the client wants to read, say in this example, 4 records, then each bucket only contains at most 2 of the client's input indices. And so now the client can kind of send its queries to the server. It will just send 2 queries for each bucket, and it will insert its it will use this query to query the indices it's interested in. So here in the first bucket, the client's not interested in any of the records, so it just puts in some dummy queries, again, to avoid any leakage. And then in the second bucket, the client's interested in the first and the second record, so it just runs the PIR scheme on index 1 and 2 on this bucket, and so on and so forth. And and notice this thing works only as long as the client makes all those queries at once. So we assume that this is kind of a non-adaptive batch of queries. You get Q inputs. The client generates the queries to read those Q inputs and sends all of them together to the server. The server responds to all of them. Basically runs the answer algorithm on each query on the correct bucket and sends the responses back to the client. So let's see what does this buy us. So first of all, in terms of correctness, we said that with high probability, each bucket will not overflow with inputs, so the client will be able to fit in the inputs into the buckets, and the correctness will then follow from the correctness of the base PIR scheme. And again, I should mention that we can apply this trick both in the single server and in the multi-server setting. And then the security will just follow from the security of the base PIR scheme. Basically, what the server will see, it will just see lambda log n queries for each bucket, and regardless of the client's input, and those queries, it's in the same number of queries for each bucket, and the queries hide the inputs just from the base PIR scheme. So this gives us security of the scheme. And the interesting part is the efficiency. Let's just look, we can analyze the communication as well, but I didn't want to overwhelm this with too much computation. Let's just look at this parameter of server time that we want to compute. So what we'll have here is the total amount of time that the server will need is Q, which is the number of buckets, times lambda log n, which is the number of queries per bucket, times the time it takes to run, the answer algorithm on a database to run the answer algorithm on one query on a database, on a smaller database of size n over q. And even if the base scheme has linear time, so this last term is just n over q, we get here that the total time of the server is n times lambda log n. And notice this is independent of Q. So if you compute, the time per query, now it becomes something like n over Q times lambda log n. And this term lambda log n, you can actually improve it with using better encoding than this random bucketing that I've described. But the key point here is that now you get roughly n over Q work per query instead of n. And the way where you're paying is that you need to run Q queries at once. You cannot just send them one by one and expect to get the same benefits. Yeah, that's the batch PIR approach. Cool. The second approach is slightly different, and it tries to another classic approach that tries to improve on this constraint that you need to have a batch of queries ready at once. And this is called PIR with preprocessing. And the main idea here is that the servers will save on time by pre-computing the responses to all possible queries of some standard PIR scheme. So the server will take the database and will encode it, relative to some PIR scheme by storing the explicit responses for PIR queries on that database. So let's say the server does this offline in a pre-processing step. It just simulates all possible queries of the base PIR scheme, runs the answer, and stores the response. And now in the online phase, when the client sends its query, the server just can look up the answer from this huge table of responses and send the response back to the client. And notice that now it's just reading one element from the table. It doesn't need to read the entire database. This can be much faster than the running the PIR scheme on the base PIR scheme on the original database. So let's just see the efficiency of we get of this approach. So let's assume if we have a base scheme that has communication, upload U of n and download D of n, then the new scheme will the new scheme will basically have this now the space, the storage on the server grows. Now it needs to store this full lookup table of responses. The size of the table is 2 to the U of n because it's all possible queries, and each record is D of n, the size of the response of the base scheme. But the online time is now super fast. You just basically read one element from this table. You can think about it as kind of U plus D, just reading the inputs and the outputs. And concretely, let's see what we get if we plug in some PIR schemes. So let's start with the 2-server case. Here, even the scheme that we've seen, the square root n scheme, would give us a PIR with preprocessing scheme that has space 2 to the square root of n, and time would be square root of n. So much more efficient, but obviously a large storage cost. And if you plug in better PIR scheme, in particular, you want, the key thing is we want PIR scheme that have very low query size, so very low upload. And there are, in fact, such a scheme. If we take schemes that have logarithmic upload size and the size of the response is something like n square root n plus something, so n to the 1/2 plus epsilon, this would give us a PIR with preprocessing scheme where the space would be poly n, right? Because it's 2 to the log n, or the log n. This would be a polynomial storage rather than the 2 to the square root n in the basic scheme. And the online time would be a bit larger than square root of n. So very, very cool idea. It significantly reduces the online time. The problem is that this polynomial, so the constant in the log n and the polynomial here in the size of the storage, they're still quite large. And this is annoying in practice. So if you want to get something like n to the 0.6 online time, you end up with something like a cubic blow up in the size of the storage. And if you have a database with gigabytes in size, then cubic would be prohibitively high. That's kind of the two approaches, the two classic approaches to reducing computation of PIR that I wanted to talk about. Any questions about those?
No questions till now.
Fantastic, great. Okay. So I also want to mention that here I gave this classic work of Beimeli and Malkin. I talked about the 2-server case, and much more recently there's been much more activity on trying to develop the analogs in the single server setting, where these are schemes that are called doubly efficient PIR schemes called Panda. They try, but I think in the single server thing they also face this barrier of the storage on the server being very high. So the cost of increasing the online time is pretty high in all those schemes. Okay, and so maybe for how much time do I have left in this first hour?
About 10 minutes. 10
minutes. Okay. So I can start off with the more recent approaches, and this is where I'll talk a little bit of some of the things me and my colleagues have been working on over the past couple of years. So we'll basically start off by introducing a different type of model that tries to reduce the computation for PIR. And this is the offline-online model, which I'll present in the two server case. We'll talk to them, we'll refer to them as the left server and the right server. And in this model, the client first runs an initial offline phase in which it talks to one of the server and obtains a piece of information about the database, which we call the hint. And the size of this hint would be sublinear in the database side. Otherwise, you can just download the entire database, and you can think about it as being as roughly square root n. And generating this hint will still take a lot of computation for the left server. It will still require the server to run in linear time. But the nice part is that the server, this left server, will only have to run this offline phase once per client. And then the client will be able to run many queries more efficiently. So after downloading this hint, the client stores this hint locally. And then when the client wants to read an index from the database, some index I, it uses its locally stored hint to generate a query to the other server, to the right server. And crucially now, both the amount of communication and the time it takes to the right server to respond to the client's online query will be sublinear in the database side. So this will be much faster. And in the end, the client recovers its bit of interest. And I should just say again, the comparing, say, to the batch PIR approach is here the client can repeat this online phase to read multiple items adaptively. So it can read item 7, then it can get the response. Depending on that, maybe read item 10 and so on and so forth. And we don't need to commit to a non-adaptive batch. And I should also mention that kind of a similar offline-online model has also appeared in some works before, but I think in prior works, usually it either required a lot of storage for the server or the online time was still fast. And here, notice that in particular, the two servers, they just store the database in its original form. So if we compare it to PIR with preprocessing, here the servers the storage on the server doesn't increase at all. They actually just store the exact database. The client now needs to store this piece of information, the hint. This would be sublinear. And yeah, that's kind of the comparison to PIR with processing. And we said the comparison to batch PIR is that now we can do things non-adaptively. Sorry, we can do things adaptively. So let's maybe now see what type of schemes can be built in this model. And I'll just talk about that kind of this ignore for the remaining of this talk. I'll usually ignore polynomial factors and the security parameter lambda and polylog n factors where length n is the length of the database. And in the two server setting, we can actually build offline-online PIR scheme with communication square root n and square root n online time. And this is from a very mild assumption, just from the existence of pseudo-random generators. In this scheme, the client will use square root n time, and also the size of the hint, the amount of storage that the client will require will also be square root of n. We can use PRPs to achieve that. We also can get efficient offline-online PIR in the single server setting. So here we have two options. We can either settle on slightly higher complexity, so n to the 3/4 online time. And this we can build from a wide range of public key assumptions like DDH, DCR, and others. Or if we're willing to use heavier tools, if we want to use FHE, then you can actually get the same you can recover the same bound. You can get square root n just in the two server case. And another nice benefit of those single server offline-online PIR scheme is that they actually, unlike regular single server PIR, they don't require any public key operations. They don't require the server to make any public key operations in the online phase. So it makes it even concretely more efficient. So both asymptotically, you can get something like square root n and to the 3/4, and this will be just no public key operations. The offline phase, of course, will still contain public key operations because we know that you can get single server PIR without public key crypto. And if we have some time at the end of the next hour, I'll describe the lower bound that shows that with in a specific regime, then those bounds that we get, they're optimal. So in fact, any online PR scheme that stores the database in its original form and uses communication C and online time T, the product of the two must be greater than N. So you can see the square root N schemes, and in the two server case, or from FHE in the single server case, they're optimal for schemes that store the database in the original form. If you're willing to encode the database, like in pure with preprocessing, then you could do better. Cool. Okay, I think actually this would be a good time to stop. And then after the break, in the next hour, I'll start by presenting the construction of these schemes. Maybe there are some questions left about the model and the results for offline-online PIR.
Yes, so there are several questions. So the first question doesn't deal with the offline-online PIR model. So it's about PIR with preprocessing. What's the complexity of updating the database after the preprocessing is done?
Oh yeah, this is a very good question. We'll see this applies also to offline-online PR. So whenever we need to preprocess the database, then these things needs to be taken into account. Then so I think naively you would need to rerun the preprocessing algorithm, right? Because potentially every query, you store those responses. And those responses potentially, as we know with regular PIR, every response kind of requires touching every bit of the database. So if you update the database, you need to recompute the preprocessed database.
Right. So next question about offline-online PIR. So is it possible to get information theoretic offline-online multi-server PIR, and if not, why not?
Yeah, that's a very good question. We actually, you can actually get PIR with statistical security. So we don't get quite perfect security, but you can think about it as PIR with information theoretic security and a small failure probability, like a tiny failure probability, and you can do it like without any assumptions. I think in some settings you might end up paying a little bit more in communication, but generally the answer is yes. And you can check out the paper for the details.
So last question. So the benefit of the online-offline scheme is that after the offline phase, the left server doesn't have to do more computation while the client can do multiple queries.
So I would say that the main benefit is that you can, after running this expensive offline phase, any subsequent queries, and you can run many queries, the servers will be able to respond to faster. And in some of our schemes, you can actually only the right server needs to be involved in the online phase, while in others, both servers still need to be involved, but the collective amount of work is smaller. So I would say that the main benefit is reducing the amount of work. And even if you take into account the expensive linear time offline phase, if you're doing enough queries, then you can amortize this over many queries, and so you can think of the cost per query, the total cost per query would be sublinear or something like square root 10, say, specifically.
Okay, that's all.
Cool.
Okay, thank you very much, Dima, for the very interesting talk. And we'll have to wait until after lunch to find out how your constructions work. So we're taking a lunch break now, and we'll be back at 2 p.m. Israel time.